These high energy compounds we're talking about, which are the currencies of cells, why do they release so much energy? Why is it that the hydrolysis has large negative gives free energy change? It is because of the high stability of the products. Remember, everything naturally needs to be at rest. And so these high energy compounds with so much energy stored in their bonds need to break down so they can become very stable. Now, how come their products are very stable compared to the high energy compounds that produces them? We have four reasons for that difference in stability between the high energy compounds and their products. One of them will be electrostatic repulsion relief. Remember that in ATP we have four negative charges. Four negative charges. Remember your adenine hooked up to your ribose 5-phosphate. And then here you have your phosphate bonds. 1, 2, 3. You have your 3-phosphate bonds for ATP, and then you have your sugar. And then you have your adenine, ATP. So we have there's an oxygen here. 1, 2, 3, 4 negative charges. But when you come to ADP, when this is broken down, it gives us ADP. And ADP has just 2 phosphate groups. And then you have your CH2 on your sugar. And then you have your adenine base here. So for this, we see 3 electronegative negative charges in ADP and 2, 4 in ATP. 1, 2, 3, 4. So we see that the like charge repulsion in ATP is higher than in ADP because the number of negative charges are lesser here than here. We know that like charges, they repel. Think of this like a crowded room with negative people that are angry. When you have 4 angry persons in a room, a locked up room, the tension will be more than when you have just 3 angry persons in a room. If one angry person goes away, the tension in the room reduces. So, reduction in electrostatic repulsion can account for the higher stability of ADP than ATP. This different stability will favor the breakdown of ATP to ADP. So it favors the reaction going forward. Another reason we can give for higher stability of products of high energy compounds, and the reason that the forward reaction is favored is another example will be resonance stabilization. What does that mean? ATP is broken down to ADP, lysis to ADP, and inorganic phosphate. The phosphate in ATP cannot change its form, cannot resonate, but the free inorganic phosphate that is released can exist in 4 possible resonance forms. This is phosphate, it can also be this, it can also be this, it can also be this. Now phosphate has an hydrogen, and the hydrogen is outside. You can see the difference between these forms are just in the position of the double bond. Here, the double bond is up here, Here it is by the left, here it is at the bottom, and here it is by the right. So the fact that phosphate, inorganic can exist in 4 different resonance forms makes it highly stable, favoring the reaction towards this direction. It is impossible for this phosphate group to combine with this immediately to give this. So because of the high stability of the phosphate during the hydrolysis of ATP, it favors the reaction to the right, meaning that the breakdown of ATP becomes very easy because it produces very stable products like inorganic phosphate. So this means that resonance stabilization is another reason for the very significant difference in stability between high energy compounds and their products, which favors the release of large amount of energy available for cellular work. Now the next